What was that? Is this? Yeah, I think it's working. I don't know. I can't hear it. That's all right. Kappa is back. I have. I know that I am going to be inviting challenges for the next couple days, but last night I uploaded all of the files from Chem 105 from last semester. So if you were in Chem 105 last semester, you are now in the Chem 106 class as well. I think your password is either exactly what it was before, or the other possibility is that your password for all of you is Spring08, which is what I tried to make it, but I don't know that that worked. So it's spring semester 2008, that's where that came from. If all else fails, if you get the failure, the challenge that says it won't let you log in, go back to the login screen, and I'll put a link on the Blackboard page so you can go right to it. Go back to the login screen, and then where it says forgot password, go into that page. Your email address that I used is the one from last semester, which is your case ID, in my case MJK56. So your email address would be that one. It'll ask what's your email address, and then it will email to you a link to allow you to update your page. Now, we will probably overwhelm the system again. I expect to get lots of emails from people saying I can't get in. Please give it 24 hours before you panic. But I'll show you what the problems are so that you can work ahead. There we go. Navigate contents. Why does Kappa have the NBC logo? I have no idea. That's what it loaded for me. I don't even worry about it. I just have it as a shortcut on my menu bar. There are currently only 4 problems built in there. They are problems 5 and 6 from the text. This is a chapter on buffers, chapter 17. Problem 9, problem 13, and problem 20. So you can actually go in the book and do those problems. The fun one, of course, is this last one, which says, okay, here you've got some mass of an unknown monoprotic acid. It takes a certain amount of this known concentration base to titrate it to the equivalence point, figure out the molar mass of the unknown acid. Oh, and by the way, if you do this experiment not all the way to the equivalence point, but part B says if you add some amount less than the amount needed to get to the equivalence point, the pH is, in this case, 5.27. What's the pKa, or what's the Ka for the reaction? So these are right out of the book. The only change that has been made is Amelia asked me to modify the wording on one problem, which was this one: which of the following systems can be classified as a buffer system if you assume that both are in relatively equal amounts? So she was adamant that that one was worded incorrectly. So do try to log in. Those of you who were in Chem 111 last semester, drop me a quick email sometime today to ask me to upload you into the 106 class roster. Send me a password. Well, actually, I'll just try to make your password Spring08 so that it's set. And then those of you who weren't in 105 or 111 and you're in this class, welcome, if I haven't said that already. Send me an email to that effect so that I can put your data in there. So those of you who want lessons in Kappa, again, we'll do a work through at some point. So oh wait, I should have shown, that one said when it was due, right? Next Wednesday. It's due the day before your test. It's due in the afternoon of that day so that you can do it before the help session on Wednesday night. And the correct answers will be posted to the Kappa site before the help session Wednesday night. So if even after looking at the answer, you still don't understand it, you have something specific you could ask them next Wednesday night. I will be doing a few more problems on KSP and KF. I will have those up before Friday. Hopefully they'll be up tomorrow. So look out for that one, and we'll do the same thing. The due date will be the same on those. They're intended as practice, so it's just something for you. And I also got to start collecting some points for your homework grade. So let me close that. All right. I can't remember how to do it, so. All right. Formation constants. These are yet another equilibrium constant. But what we're talking about those of you in lab will like this. Is that we're going to talk about forming complex ions. And these are ions that have coordinate covalent bonds in them. Okay? A simple ion would be something like a chloride ion or a calcium ion, something that is just an element from the periodic table that has a charge associated with it. Other simple ions that are not monatomic but might have multiple atoms in there would be things like ammonium ion. We learned several polyatomic ions, nitrate, carbonate, sulfate, hydroxide. These are all simple ions. They are just, they only consist of covalent bonds. So OH minus is an oxygen covalently bonded to a hydrogen. Sulfate is a sulfur atom covalently bonded to 4 oxygen atoms. In a complex ion, you're going to make something that has a coordinate covalent bond. And if we go back to what the definition of a coordinate covalent bond is, it's a chemical bond where both atoms, or excuse me, electrons, both the electrons in the bond come from one of the participants in that ion. Okay? All chemical bonds have 2 electrons. A complex ion chemical bond, I brought the wrong pages with me. Oh well, that's all right. We'll just come up with one from memory. Would be something like this one. Tetrahydroxy zinc 2 ion. I haven't spent a whole lot of time on naming, but I'm going to do it a little bit here. Tetrahydroxy meaning that there are 4 hydroxyls as part of this complex ion. The zinc that is in it itself is a +2 ion. So this is a zinc 2 plus ion plus 4 OH minuses combined together to give you that compound, that ion. All of the electrons in the bonds of this thing. This one, I mean, what's the geometry of this, do you think? It's obvious. Tetrahedral. There's 4 things attached to the central zinc. So this would be a zinc ion with 4 OHs hanging off it. And if we remember the OH, it looks like that. It's got all those lone pairs of electrons on the oxygen that it can contribute to the bond. And so each one of these chemical bonds corresponds to the pair of electrons coming off of this. In terms of Lewis acids and bases, what is the hydroxide here? What is hydroxide anyway? It's a base. It's a Lewis base because it's an electron pair donor. So this is an example of a Lewis acid-base reaction where the zinc ion is the Lewis acid and the hydroxide ion is the Lewis base. The zinc accepts the hydroxide ion's pair of electrons. Now, these compounds can also exist if you take neutral ligands. The thing that's attached to the central metal. They all involve a metal at some point. But they'll take either an anion to be attached to that metal ion, or they'll take a neutral compound like ammonia to form a complex ion. You know what? Let me try that again. There's some debate as to whether there should be one A or two there. Hexaamino or hexamino, I prefer two A's. There are 6. The amino is the ammonia ligand or thing that's attached to it, attached to that central cobalt. In order to have a +3 charge on this whole thing, we start with a cobalt ion that has a +3 charge. We add 6 ammonias to it, and we get the complex ion. Okay? Some of the other definitions that you got when you did this in lab were things like ligands, polydentate ions or dentate ions. Those of you who are pre-dent know what dent means in this. It has teeth. And so a polydentate ion is one that grabs on in more than one place. Ammonia has a lone pair of electrons in it to allow it to form a single covalent bond with the cobalt ion. There are other compounds that have more than that. The difference between these ions and simple ions is that these ions have coordinate covalent bonds, where simple ions don't. They simply have covalent bonds. A coordinate covalent bond is a chemical bond where both electrons come from one compound, and now I'm going to call that compound a ligand. Okay. This is an interesting one. It's abbreviated EDTA. EDTA is ethylene diamine tetraacetic acid. So it's 4 acetic acids with this ethylene diamine, whatever that is, surrounding it. How are you at drawing this one, Amelia? Not at all, she says. I'm sorry? I got to make 4 bonds in here, So there's a double bond there. No, it's not. Yeah, there is. This thing has multiple places where it can connect onto a metal ion. If you look just at the acetic acid part of that, the acetate ion up here, remember what the end of the acetate ion looks like. And with a minus charge, it would look like this. So that's the acetic acid part of this thing. And this pair of electrons that is out there can glom onto a metal ion. Usually this ion or this ligand reacts with divalent metal ions, so like lead ions, zinc ions. If you look at any of you who happen to have picked up something from the deli, and if you look on the ingredients list of any bread product, you will find EDTA listed. EDTA is put into bread products in order to grab onto any metal ions that might be in there. And they will complex with those metal ions, and they'll wash right through your system. If that EDTA wasn't in there, the divalent metal ions that you ingest could replace iron in hemoglobin. And so divalent metal ions can be very harmful. And so to put the EDTA in there,
What metal is in your bread, Dr. Kenney?
you tell me what metal's in the bread. Lead is in your bread? Calcium, zinc? Seriously. They're all in there because the other place they come from is some of the other preservatives that are in there use metal ions as the cation. Go read the ingredients on bread. It's scary. You'll see EDTA in lots of different things. But the nice thing about this, EDTA is in your soda? Is that a lot of these ions with multiple binding sites allow C2O4. C2O4, if you draw the dot picture for, looks like this, where we've got a minus charge here and a minus charge here. Where you end up putting the minus charge on an oxalate ion doesn't matter, because if you look at that central bond between the two carbons, it's a single bond, so this thing can spin around itself. It's free to go whichever direction it needs to go there. If it were a double bond, it wouldn't be able to spin, but because it's a single bond, those CO2s on either end can rotate however they need to. The reason why that's important is because when you take this and you combine it with a +2 metal ion, is you can take this bidentate ligand. It's bidentate because it has two places where it can form coordinate covalent bonds. And we can bridge those two things. So this thing right here is a C2O4 ion. Okay? So there's three of them on here. So this would be an M C2O4 3. And the charge is going to be, let's see, -6 and +2, 4 minus of this compound. And there's a very fun thing about this compound. I'm going to make one of these. So we'll make the one that's there. Okay? So I've put 3 oxalate ions onto that metal ion, and I've put them in a certain way. So I'm connecting the one that's sticking out front and going back here with an oxalate bond. I'm connecting the one up here with the one that's going out there, so there's an oxalate bond here. And then I'm connecting the one that's down below with the one back there. That's what that picture's showing. Now draw the mirror image of it. All I've done is if you were to put this thing up against a mirror, what would it look like? So over here, the C2O4 bond is on those two. It's from the front down to here, and it's from the bottom to the back position. Actually, I have it the other way. Front to the back. I'm getting my back and front mixed up. Okay? Are those two things the same thing? Let's try it. I'm going to rotate this one now by 180 degrees, about that axis. Okay, so I'm going to take it and I'm going to spin it along that vertical axis. So if I do that, what happens? This oxalate ends up here. This one that went from the top to a back position, when I rotate this 180 degrees, this back position ends up here. So what was here is now going to end up here. What was in the front moved to the back when I spun it by 180 degrees. So I have another oxalate. It gets really ugly. Going there. So this is just a rotation from here to here. This one's the mirror image. The question now is that and that the same thing? No, they're not. It's just like your hand. Your right hand, there's nothing you can do to rotate your right hand in any way, shape, or form to make it look exactly like your left hand. It's a mirror image of it. Now, this isn't true of all things. If I take carbon tetrachloride, a tetrahedron, and I do the mirror image of it, I can simply rotate it and get the same thing back again. This works with these kind of compounds. And so because they have this right and left-handedness to them, one of these will rotate polarized light to the right. The other one will rotate polarized light to the left. Now, seeing as you all just finished an exam, you all know that that's rather important. The rotation of a DNA helix is critical. If it rotated the other way, you'd have a completely different compound. And so the rotation of these, or the handedness, is important. And when it comes to pharmaceuticals, when you go to design drugs, if you make a drug that looks like this, one form of it will do what you want, the other form will do something completely different. Hopefully, it will do something that is useful, but quite often it does something harmful. Or it may do nothing at all. And so one of the biggest areas of drug synthesis right now is figuring out how can I make these molecules so that I get all of this rotation and none of this. Because if I make them both, what do you think? What can you tell me about their chemistry, do you think? Where does the chemistry occur? In the electrons. What can you tell me about the electrons of these two compounds? They're identical. What do you think is the chemistry of these two compounds? They're identical. They have exactly the same chemical properties. What's different is how they interact with things that also rotate light. And so if you make these things, the odds are good you're going to get a 50-50 mixture, but only one does the thing you want. Guess how you separate it? You take a tweezers and a microscope, and you pick out the crystals you want. And you take the crystals you don't want, and you throw them back in, and you recrystallize them to hopefully get more of the ones you want. What do you think that does to the cost of that drug? It's huge. And so if someone could figure out a way to synthesize these drugs, hi, Dad. Excuse me, let me talk to my daughter for a second. That is Randy. No, she's on break for 2 weeks. Is she the one what? They're both swimmers. She's the one who won the backstroke. So, sorry about that. Anyway, in terms of drug synthesis, if you could find a way to synthesize the drug that you want with the orientation you want so you don't have to hand separate it, all of a sudden your drug company can cut the cost of that pharmaceutical significantly over everybody else. But guess what? You're still going to charge an arm and a leg for it because everybody's been used to paying an arm and a leg. You just do it an arm and half a leg. And you're going to make money hand over fist. And so there's huge research projects working on this.
You said that metal was a bidentate?
That metal is a bivalent metal. Bivalent. It was a +2 metal. Okay? It's not, and so bidentate would mean it would have 2 teeth. The oxalate is a bidentate ligand. Okay? Now, the great thing about these things is if I take this zinc tetrahydroxide compound, we can write an equilibrium constant expression for the formation of this ion that looks like that. It's just like any other equilibrium constant expression. Now, somebody have their book handy? I can't remember the KF value for this, so I have to make it up. Susie doesn't have it? Okay. I'll make it up. All KF values, it is. Do you got the chapter there? That works perfect. I brought the wrong pages. Thank you. You have chapter 18 here too. Working ahead. All right. KF, zinc tetrahydroxide, is, I want you to know I picked one that's underneath the, oh wait, wrong one. There it is. Wouldn't you know I picked one that's not in there? All right, let's pick this one then. All right, zinc ions plus 4 ammonia to give tetraamino zincate with a +2 charge. KF once we know the balanced equation, we can write the equilibrium constant expression. And the value of KF for this is 2.9 times 10 to the 9th. All of the complex ions that are listed in table 17.4 have values. The smallest value here is 10 to the 6th. The largest is 10 to the 30th. 10 to the 41st. So these things form very easily. So here's the question. I'm going to make this easy. you. What is the zinc ion concentration when you mix 1 liter of 0.2 molar zinc nitrate with 1 liter of 0.2 molar ammonia? And typically when we've done these, we've taken the balanced equation, we've set up our equilibrium table. Oops, that one I need. I can't ignore it. We're going to follow the same process we always do. So Kf equals x over is that the number? I'll be right back, thank you. I can scroll back. How far? There? That one? Okay, so Kf is just the concentration of the products divided by the concentration of the reactants, all raised to their stoichiometric coefficients. The value is about 3 times 10 to the 9th. We set up the problem, and now how do you solve it? Those of you with your TI-89s will just program them in there and do it. Where did I get 0.2? Sorry, where did I get which? How did I get the 0.2 ZN2 plus? Then I'll get that question over there. I started with 0.2 molar zinc nitrate. And so why did I pick on nitrates? Because I have 0.2 molar zinc nitrate and 0.2 molar ammonia, right? Okay, then I'll get go back to your question. Yours is another one. Hang on for a second. So where did the zinc ions come from? They came from zinc nitrate. Why did I pick on nitrate? I'm going to pick on nitrates a lot because all nitrates are soluble. So as soon as you see a nitrate compound, you should be thinking, I don't care about the NO3, I care about the other stuff. Okay. Now, you asked me why. Nope? Okay. So, how would you solve this? Those of you, as I said, with TI-89s will just put it in solver mode and solve for x. Those of the rest of us who don't have that calculator, you sit here and you say, okay, what's the other ways we do it? Well, I could solve a quadratic. Well, there's not a quadratic equation. It's x to the 4th. It's going to be really ugly. The other way we do it is we make an approximation. We assume that x is small, right? Can we assume that x is small? How big is k? Big. Really big. As a matter of fact, it's so big that this thing is going to react and make lots of product. X is not small. X is huge compared to these numbers. It's going to practically react 100%. So I used to teach students to solve this problem saying, okay, why not just flip the equation around and do it backwards? Well, you can do that. There's nothing that says I can't do this. Right? I can write the reaction backwards. And if I write the reaction backwards, I can write an equilibrium constant expression for it. Do I know the value of k? If you take the reaction and you turn it around, what do you do to k? 1 over. So yes, I know the value of K. So if I take 1 over 2.9 times 10 to the 9th, what do I get? I think I get 3.3 times 10 to the minus 8. If I did my math right. 1 over 2.9 is about 0.33 times 10 to the 9th is 3.3 times 10 to the 8th. Yeah, I think that's right. So I think that's about right. So I do it this way. I'm going to do the reaction backwards because then when I do it backwards, now since K is so small, the amount of product I get is going to be small. Well, how do I assume how much product? Since Kf was so large, we're going to assume that the reaction went to completion. So I took all of the zinc ions I had and all of the ammonia I had, and I made as much zinc ammonia compound as I possibly could. Guess what? It's a limiting reactant problem. I told you they were going to come back at you. If we go back up here and we say, oh, look, we started with 0.2 molar zinc ion and 0.2 molar ammonia, but there's a 1 to 4 ratio there. So the fact that I started with the same concentration and the same volume, so I did that intentionally, the same number of moles, how much ammonium compound, zinc ammonia compound am I going to make? What's my limiting reactant? I need 4 ammonias for every zinc that I've got. And so since I started with the same amounts, ammonia is going to get used up. How much zinc ammonia compound will you make then? 1/4 of what you started with. So the initial concentration here is 0.05. And actually, because of the way I wrote the problem, it's in 2 liters. Right? I mixed a liter of each compound. If I figure out how many moles of each there was 0.2 moles of each. And so when I do the reaction, I end up with 0.05 moles of product, but now it's in a 2-liter volume. So its concentration had to be, the dilution had to be accounted for too. How much ammonia will I have at this point in the reaction now? That's a good answer. You're right. None. I used it up. It was my limiting reactant. See, I can even build in the yawns. That's all right. It's my limiting reactant, so it's gone. Now I just have to figure out how much excess zinc ion was there. Well, I used 1/4 of it, the 4-to-1 ratio, so there's still 0.15 moles of zinc ions. And again, it's in 2 liters. I think you're starting to see, okay, why did he keep harping about limiting reactant problems? They come back to us all the time. Do those numbers make sense? Everybody got those? No. It's all right. If you don't, we'll just slow it down. Come back up here and look at what we got. This is 0.2 moles in 1 liter. 1 liter, I did that intentionally, so there's 0.2 moles of zinc ions. If I used up all the zinc, I'd make 0.2 moles of this, but the total volume would be 2 liters because I mixed 1 liter of each together. I don't use it up. Instead, I use the ammonia up. For every 4 ammonias, I get 1 zinc compound. So that's where the 0.05 came from. And so our limiting reactant was ammonia. It got used up. We still have leftover zinc. That's okay. What's going to happen? Some of this is going to react. You're going to make some more of this. And you're going to make some of that. 0.05 divided by 2. 0.025, right? So I get to this. K equals 0.075 plus x plus 4x to the fourth divided by 0.025 minus x equals 3.3 times 10 to the minus 8. Bless you. So again, we have this ugly looking equation to solve, but we're going to do what we've done every other time. If k is very small, which it is, we're going to assume that x is small compared to any changes that there might be. So that means I can ignore the x here and here. I have to leave it here because it's only 4x. So k is approximately equal to, you can put your calculators away, you aren't going to need them. Because if we wanted to, we could solve for x now. It's not that hard. You could all take a fourth root on your calculator, I hope. But guess what? You don't need to. Go back and ask what was the question. Emma? It wasn't negative ninth, it was positive ninth. That's what. Okay. I'm sorry? You think it's to the minus 10th? Okay. I'll make it minus 10. I can live with minus 10. I went the wrong direction. That's all right. So it's minus 10. That just makes it an even smaller number. But you won't even need your calculator. What was the original question? What's the concentration of zinc at equilibrium? Well, guess what? That's this column. If we're going to assume that x is small, what's the concentration of zinc at equilibrium? 0.015 divided by 2, or 0.075, or excuse me, 0.15 divided by 2. So it's 0.075. So you don't even have to do a calculation. Sometimes it makes sense to go back and say, what is it I want to know? You don't always have to solve for x. Sometimes you will. But if you had to for this one, it's just algebra to solve this. I think you can all do that and solve for x. And x in that case would be the ammonia concentration. Actually, x in that 4 times x would be the ammonia concentration. And the concentration of zinc ammonia compound is still 0.025 because the x is such a small number. But the equilibrium problems are exactly the same. Susie's question is, what makes this a KF equilibrium? Remember that the subscript on an equilibrium constant is simply giving you additional information about the type of equilibrium reaction. When we're talking about KF, we're talking about the formation of a complex ion. And so a KF reaction is one where a complex ion gets formed. You can write equilibrium constant expressions for any reaction. This is just one specific one. And then what we did with this was we said, okay, because this value is so large, we can't solve that problem easily. We could solve it, but we can't do it easily. So to simplify it, we're going to say, okay, because this is such a big value, we're going to assume that we make as much of this as we possibly can, and then it's going to dissociate into its parts again. And so we solved that equilibrium problem because we know how to solve an equilibrium problem where the K value is very small. So it's just a way to solve the problem in a way we're used to doing it.
And the other equation with the 2.9 times 10 to the 9, why wouldn't you assume that the 0.02 is approximately equal to 0? You just get rid of that.
That's an interesting idea. What if we do this? What if we assume, I've never tried it, let's see what happens. The suggestion that's being made is, okay, if we normally assume that x is small compared to the starting point, so that 0.2 minus x is approximately 0.2 still, What if we make the other assumption? What if we assume x is so much larger than the 0.2 that we can ignore the 0.2? Okay, we'll try it. I'm willing to try that one. So if I take this equation, and I'm going to assume that 0.2 is much, much less than x. What'll that do for us? Well, this term here, where's my highlighter? This term here now becomes negative x. This term over here becomes negative 4x to the fourth. Okay, so the negatives bother me a little bit, but as soon as you take advantage of the fact that when you take something to the fourth power, you're going to end up with a positive number, right? A negative to the fourth number will give me a positive number, so that's okay. This x here will cancel with this one here now, right? Other than a minus sign being left. And so when I solve this now, I get something that looks like that. I have no idea what this is going to do. We're going to try it and see. I think it's a good idea. Kf equals negative 1 over negative 4x to the fourth. Kf equals negative 1 over negative 4x to the fourth. So that means that negative 4x to the fourth equals negative 1 over Kf. So what's 4 to the fourth? What's 4 raised to the fourth? 256? 256? So we get x to the fourth equals negative 1 over 256 times Kf, and x equals the fourth root of that. And now is where we run into our problem. It's an imaginary number. Mathematically, we can do this, right? Chemically, no, we're not going to. So that's why you couldn't do that. It was worth a try. All right? We'll continue this on Friday.